view. This is weird. This is very strange. So let me try again. No, the same problem.
Hello, Gunta.
Hi, how are you?
Ah,
I guess, how are you?
yeah, I can hear your voice and also I can see your screen,
Okay, great.
but I'm not so
Yes.
sure if you can change it to PDF file. I can see some mailbox or something file.
Yeah, I don't know what. Usually, you can see I can put full screen, but I cannot do it. I
Full
cannot
screen.
do it right now.
Full screen. Well, but now I am seeing just the contents of your file, PC or some file.
Okay.
Maybe you can try to change to say the PDF file of your presentation.
I cannot do that. I don't know how to do it.
Yeah, but usually below you can find green button. Just below at the bottom and the midpoint. Green and with I mean your screen. Say I believe full screen mode of your Zoom.
Where?
Yeah. Then usually at the bottom central point you can find the green something like a square. Interior up upper arrow. You did not see?
No, I don't see that.
Okay, the icons, for example, mute and video, there are buttons. Yeah, left-hand side. On the screen at the bottom.
No, this is.
Oh, then something wrong.
Yeah, something is wrong. Let me connect again, okay?
Maybe, yeah.
I will try to connect again. Yes, so let me try again and share the screen.
Yeah, then once again, please look at the bottom of your
At the
screen.
bottom?
Yeah, then say, yeah.
There's a share screen. Yes, there is a share screen.
Yeah. Then
You know, I press this, but now I lost my file.
Okay. Then I don't know. I'm not perfectly sure, but usually immediately before you are clicking, please open the PDF file.
Yes. So let me now open it.
Say 5 minutes ago, I'm not so sure such PDF file appears, but please open your presentation.
Now it should appear again. So let me see share screen.
Then please click green button.
Here is the same problem.
Yeah, now fine.
Okay, well, let me just do it like this. I don't think.
Okay, good. Solved.
Yeah.
Well, so yeah, it's a great honor for me to introduce Professor Günter Ullmann, University of Washington, Seattle, and he is a president of the Universe Problem International Association and editor-in-chief of Journal of Universe Problems and Imaging. So, Günter Ullmann, please.
Okay, thank you, Maxime. So since I have only 30 minutes, I chose a topic that I can explain a little bit in that time. So this is the Calderon problem for non-local operators, a particular fractional Laplacian. So this is a Calderon, a very nice picture, famous analyst of the 20th century. And the problem that he proposed is the following. You have the conductivity is a positive function. And if there are no currents of flux or sinks of current, the divergence of the current is 0. The current is given by Ohm's law by gamma times the gradient. And you have given a voltage potential on the boundary. And you measure the induced current flux at the boundary, which is given by the normal component of the current, and that's the map. From a voltage F on the boundary, you assign the induced current flux. And the inverse problem, Calderon inverse problem, that's knowledge of this map determine the conductivity. There are many aspects, uniqueness, stability, reconstruction, numerical algorithm, and so on. I mean, in this talk, I'm making emphasis on the basic question of uniqueness. So the way it's done, it has been done for the most part, is to reduce the problem to the Schrödinger equation by performing this transformation of the dependent variables. And then then you get this problem. And actually, you can consider a more general problem given a potential Q that may be even complex. In this case, this is real. Can we recover the potential by knowledge of the Dirichlet to Neumann map, which is simply the normal derivative? So it can be reduced to that problem. As part of this problem, this is a more general problem. And then one proves a very simple identity. It has been called Alessandrini's identity, but it's very just integration by parts. Q1, U1 is the Laplacian of U1, solves the equation. Q2, U2 is the Laplacian of U2. So by using Green's identity, you get information on the boundary, which is given in this way. So you can see the potential and the Dirichlet to Neumann maps appears linearly. The nonlinear part is in the solutions, U1 and U2. That depends on the potential. So if you're looking just at the uniqueness, lambda Q1 equal to lambda Q2, this is 0. And the question is whether you can construct enough solutions so that the products are dense in the space of solutions. Okay, so I'm not going to describe this in details, but instead we're going to use a different property, not CGO solutions, which are very difficult to construct for the fractional Laplacian, but the Runge approximation. The classical Runge approximation was done for analytic functions. So analytic functions in the complex plane can be approximated by complex polynomials. And this was greatly generalized to a very general property for many elliptic PDEs. Any solution in an open set containing some set omega can be approximated using solutions in the whole omega. It's essentially a unique continuation principle that this was observed by Lux and Malgrange in 1956 independently. So you have what's called approximate controllability. And so the Runge approximation produces solutions which can be, in an open set, can be 0, and in another one, very large in the region of interest, but you have very little control outside this union set. And in the Calderon problem, has been used this type of Runge approximation for boundary determination. You can recover all the derivatives of the conductivity at the boundary by Conan-Vogelius, using similar ideas for piecewise analytic conductivities in 2 dimensions. Conan-Vogelius is, again, when you have partial data, if gamma is known near the boundary, which is joint work with Samari. And there are many other results using singular solutions, the Isakov, probe method, Ikehata, oscillating decaying solutions, Nakamura, Wang, and myself, monotonicity tests, Harrach, etc., etc. I'm not mentioning all the results and just a few of them. But the Runge approximation has been very useful property. So now let me go to the fractional Laplacian, the object of study. So we're going to consider the Laplacian to some power between 0 and 1. And this can be easily defined via the Fourier transform. You take Fourier transform of this is modulo C to the 2s. But this operator is non-local. It's in fact a pseudo-differential operator. It does not preserve supports. And the main point is that the computation of the fractional Laplacian of some function u involves values of u far away from x. And this produces difficulties, but for inverse problems it's very useful because you get that information, you get more information in some sense, and you can use that. The fractional Laplacian appears in many different models for diffusion. This is the normal diffusion, the heat equation, super diffusion, also called Levy flight in probability, subdiffusion when you have the fractional is on the time variable. There has been many works. Masahiro has done many works, for instance, on co-authors is related to inverse problem for that equation. I'm not considering that, but I'm considering the fractional Laplacian, the steady state. The fractional Laplacian is related to anomalous diffusion involving long-range interaction. That's the whole point. Levy processes in probability theory. The square root of the Laplacian is a famous Levy process. Financial modeling with jump process, etc. So there are many results for the time fractional inverse problem, as I mentioned before, but very few for the fractional in the x variables. There is a nice survey by Jean and Randell. This is a little bit old. I'm sure there are newer ones. Okay, so what is the inverse problem? Here we cannot impose boundary data, so we impose exterior data. So you have a bounded domain, and you take a potential. Now the Dirichlet problem that we solve is to solve the fractional Laplacian plus a potential in the domain omega and the data F in the exterior. And this will, as we're going to see later, doesn't have to be the whole exterior, just an open subset in the exterior. And then given an F in Sobolev space in the exterior, the S is the same as here. You look for the solution in the Sobolev space, and the Dirichlet-Neumann map, in this case, map HS of the exterior to H minus S of the exterior, and is given by the fractional Laplacian. This is the equivalent to the normal derivative in this case. I mean, it has been proven that as S goes to 1 and you go to the boundary, this gives the normal derivative. So the inverse problem is given this non-local operator and the corresponding Dirichlet-Neumann map, can we recover the potential from this information in the exterior? So the first result obtained in this direction is the following. Suppose you take a bounded open set and this is for uniqueness. Again, I'm only concentrating on uniqueness. There are some stability and reconstruction results. You take two arbitrary sets in the exterior. And if you measure the directly to Neumann map in one of the open sets, W prime in this case, for functions supported in the other one, then the potentials are the same. And the main feature that this is a local result for an arbitrary W and W prime can be disjoint or can be the same or can have intersection, doesn't matter. There is no difference between dimension 2 and higher dimensions like there is in the Calderon problem. And this gives a new mechanism for solving non-local inverse problems. So for instance, this type of results is not known in dimension 3 or higher for the standard Calderon problems. You get given the Dirichlet-Neumann map in an arbitrary open set. So suppose W prime is equal to W, it's not known whether you can recover the potential. There are some partial results, but it's not known. And so let me explain some of the methods. And this is one of the main difference. I think I will need to change computer very soon because this computer is running out of battery. And I'm out of, I didn't bring my cord. I'm in St. Louis in my daughter's house. And so the other computer has battery and I can, but you won't be able to see me because I don't have any camera on the other computer. So this is a famous result of Caffarelli and Silvestre that can interpret the fractional Laplacian by going one higher dimension as the limit of y goes to 0 of this y to the 1 minus s dy w. And it's very easy to see, for instance, in the upper half plane, when you have the x and y here, that the fractional Laplacian is simply the normal derivative in that case. And so this is the divergence when you solve the Laplacian equation, of course. You have when s is equal to 1/2, this is exactly the normal derivative. This is the square root of the Laplacian. In that case, it's very easy to interpret the Dirichlet-Neumann map. And this is generalized for any s by Caffarelli and Silvestre. And the point is that the non-local operator can be interpreted as a boundary value problem for a local operator in one higher dimension. But this, depending on the s, can be degenerate. If s is 1/2, is fine, it's the standard Laplacian. But for different s, this is the degenerate elliptic operator. So it's called with an A2 weight. And Clement estimates have been proven for this case. And the important point here, which is very different from the local operator, is that u is 0 in an open set. And the fractional Laplacian of u is also 0. This implies that the function, if it's sufficiently regular, this can be quite singular, then u is identically 0. This is certainly not true for the Laplacian. You can have a compactly supported function non-zero, that u and the Laplacian are 0 outside the support, but the function is not identically 0. So this is a very strong uniqueness result. And the way we use it is that any function in L2 of the domain can be approximated in L2 by solutions of the fractional Laplacian when the support is contained in omega and the set where the information is given. And this is in the smooth case. Yes, question?
No, everything's okay. So
Okay. And now you prove the same type of identity that we had for the local operator. For the fractional Laplacian, is very easy to prove. It's just duality. And then now you don't need to construct CGO solutions, as I pointed out, because you can approximate for anything. So this is orthogonal to any function. So you take U1 to be any function, U2 to be 1, say. And then therefore you're going to get that Q1 is equal to Q2. So this is also very different than the standard Calderon problem, because this is not true that you can approximate any L2 function by harmonic functions. Actually, the complement is infinite dimensional. But this is true for the fractional Laplace because of the non-locality. So the non-locality helps. The fact that the operator involves long-range interactions gives more information. There are many results using this technique or similar techniques. One important one is the variable coefficients fractional elliptic operators, when instead of the Laplacian here, the standard Laplacian, you have, say, Laplace-Beltrami operator of a metric, or a divergence type second order elliptic operator, which again, those type of results are not available in dimensions 3 or higher for the standard Calderon problem. The regularity and stability. You can also take one single measurement, non-local and local perturbations, and many, many results, magnetic operators, parabolic, fractional parabolic, nonlinear fractional operators, and some modification of the fractional Laplacian in some directions. Okay, so what I'm going to consider now is actually the variable coefficients. So in the case you have plus a potential, this has been solved in this very nice paper of Ghosh, Lin, and Shao. But the question of whether you can recover the conductivity itself has not been solved for the Dirichlet-Neumann map for this fractional Laplace. Again, the measurements are in the exterior domain or an open subset of the exterior domain. And you have here the non-local Cauchy data. So U in the exterior, and again, the fractional Laplacian applied to U in the exterior. So the problem here is whether one can recover the conductivity in omega from this type of measurements. There are many results for the Calderon problem. I will mention some of them in the isotropic case, but the anisotropic case in higher dimension bigger or equal than 3 in particular, there are very few. In dimension 2, it has been essentially solved in 2 dimensions. And there is a big difference when gamma is isotropic and gamma is anisotropic. Anisotropic means that gamma is a matrix. Isotropic is a scalar. And here there is a non-uniqueness. I will explain this. Any change of variables of omega, this is for the Calderon problem, for the standard Calderon problem. If there is a diffeomorphism of omega, there is identity at the boundary, then the push forward of this conductivity gives rise to a new conductivity that has the same electrical measurements. So is that the case for the non-local operator as well? Is there that invariance? And what are the results in this case? So you can actually consider a very general framework, self-adjoins positive definite operator in the following, of the second order of the following form. For all purposes, you can think about the principal part. This is related to the Laplace-Beltrami operator. And here, of course, to define the fractional Laplacian, we cannot take the Fourier transform. This is variable coefficient now. And this can be defined using the heat semigroup. This is using the spectral theorem. Can be proven using the spectral theorem. You can also use the wave equation. The heat equation is very appropriate in this case. So the fractional operator is you divide by the gamma function of minus s. This is the solution of the heat equation minus the identity applied to u divided by some power. And this converges because of at t equal to 0, this is u, so kills the singularity. And we have exponential decay at infinity of the solution of the heat equation. So this is, it's easy to show that this is well defined. Yeah, but this formula is very important for our purposes. It's very general. Yeah, so in the standard case, it coincides with the usual definition, which can also be given as a convolution. It's the inverse Fourier transform. Of course, this is a convolution. I mentioned applications of this. Okay, so what is the forward problem? In this case, it's the same as before. You have an open set, and you have omega, and you solve the equation in the open set, and you give data on W tilde. And the Cauchy data, which is the partial Cauchy data because it's not information in the whole exterior, then is U restricted to this open set, and then you take the fractional Laplacian on the other open set. They can be disjoint like in this picture, but they can be the same, or they can be an intersection. So this is the problem. What can we recover about the operator L? So this is the question. And what we prove is the following. So suppose for simplicity that these two operators, you have two elliptic operators on this form, which are self-adjoint and positive, so you can define the power. And assume that outside omega is identity, although you can assume the same metric, that the same coefficients that are the identity at infinity. Is that enough? And the theorem is that for the non-local problem with partial data, you can recover the Cauchy data for the local equation. The Cauchy data for the local problem is, this is the standard one. So these are the operators, not the fractional ones. Case here is 1-to-1. You have two operators in omega. So you can go from the non-local data, which can be partial, to the whole Cauchy data for the local operator in the whole boundary. So all the results that we know for the standard Calderon problem can be proven then for the non-local operator. An important case is the Laplace-Beltrami operator. So in this case, this appears naturally in Riemannian geometry. But in Rn, you can think that this is just a positive definite and symmetric. And is the, I'm running out of time. And is the Euclidean metric outside. Again, I repeat, this is not completely necessary. It has to be the same and be the Euclidean at infinity. This is the Laplace-Beltrami operator in coordinates. And so the result implies this. In particular, if they are isotropic, then we know by theorems that have been proven for the isotropic case in any dimension bigger or equal than 2, then the metrics are the same. if it's anisotropic, there is a gauge invariance. So let me explain. This is related to what's called transformation optics in clocking. You take a smooth map of this identity in the exterior. If you change variables for the heat equation, then you're going to get a new heat equation with the new coefficient being what's called the push forward of this matrix A. So, you take this, for instance, the fractional Laplacian, you take what's called the push forward of this, which can be obtained just using the chain rule, like when you change variables in the equation. Then the Cauchy data for the metric G is the same as the Cauchy data for the pullback of the metric G. So there is the same invariance as we have for the standard Calderon problem, because the heat equation has that invariance, and the fractional operator can be defined via the heat equation using this process. Okay, so I don't have time to go over the proof. I'm running out of time. But let me mention a new result. So this was explaining all the results known in the two-dimensional case. But let me explain a new result for a closed Riemannian manifold, and you take a positive definite metric. You take again the fractional Laplacian defined as before. This makes sense. And you consider what's called the source to solution map. So you take F supported in some open set of the Riemannian manifold, and then you take the solution in the whole manifold and restrict it to the open set. If we don't have a boundary in this case, it's called source to solution. This is the source F, you map it to the solution. And we just proved the preprint is in the archive, was posted in the archive last week. So from the fractional operator, we can determine the metric up to change of variable, which is the identity in the open set. So this result is absolutely not known for the Calderon problem. In general, this is true for any dimension bigger or equal than 2. And the idea of the proof is to show that this information I'm not going to go through the proof in general, but you can get the heat equation. So you can get one extra variable on the open set. This is partial data for the heat equation on the open set. Once you have that, it's known that you can recover the metric up to a change of variables. This follows from the result of Kurilev, Belishev, Tataru, because you know the heat equation, you can get the wave equation, and this result was proven a very deep result of Kurilev and Belishev using the boundary control method that uses this famous unique continuation theorem of Tataru. So you get the heat equation, and from the heat equation, you prove this result. Okay, I think I'm running out of time. Let me finish with that. Thank you.
Okay, thank you very much. Colleagues, any questions?
Nobody understood anything? It's plumbing.
Professor Ullman, could you please tell me if, for instance, we have partial derivative with time and partial derivative, fractional derivative with time and fractional derivative with space. Are there any theoretical results in this case?
I don't know of any, but that will be an interesting problem, right? I don't know what the physical model will be in that case, but you mean here to take a fractional and fractional here, in both?
Yeah.
That I don't know. I don't know.
Rather smooth physical process should be.
Yeah, okay, that will be an interesting problem. Yeah, we haven't looked at that one.
So, okay, do I understand right that there are no theoretical results in this case?
Yes, yes. That's up to my knowledge, which is not complete.
Okay, thank you. Well, colleagues, any other questions? Well, if there are no questions, so Professor Ullmann, thank you very much again
Okay.
for your interesting talk. So thank you.
Thank you. Bye.
Well, and
I'm running out of battery, so I will go to my other computer. I will come back, okay?
okay,
For Clement's talk. Thank you.
Okay, thank you. Well, and the next speaker is Professor Clement Stefanov.
Yeah, thank you very much. Let me share my screen. Okay, you can see it now?
Yep.
Okay, good.
Yeah,
Okay, so, yeah. You want to say something?
So let us start.
Okay, thank you very much for the invitation. So I'm going to talk about inverse problems for semi-linear wave equation, which is a joint work with Antonius Operator, which is a colleague of mine at Purdue University. It's actually based on two works. Okay, so let's start with the semi-linear wave equation of this sort. And the dimensions are 2 and 3, okay, because it's just more convenient. So we assume that the support of f is compact with respect to x, which is not really heavy assumption, but it's very convenient. Not really important, but properly. And the inverse problem is to do the following. You want to reconstruct f if you, from the following information, you send some waves through the domain, and the waves go on the other side, roughly speaking. And then from this information, you want to understand what's happened, what is inside. So here's some cartoon of that. So this is support of alpha. Okay, instead of alpha, that should be f. It's going to be alpha in a moment. That is support with respect to x. And then you send a wave, and then the wave goes inside, and then it exits, and then you measure what is on the other side, and you want to determine from that the nonlinearity. So I can give a very short version of the talk, which basically describes the results. If f is the nonlinearities of cubic type with a unknown coefficient alpha, then actually you can do it by using solutions which are not really small. H is a small parameter, so the solutions actually grow with h. And you can do it in an explicit way. You get a phase shift, and that phase shift gives you the exit transform of alpha, and you're done. And if f is odd, now I'm going back to this more general case, if it's of this type, and then you can use solutions that are not really large, right? And the amplitude is, roughly speaking, 1 of order 1, and you can still do that in an explicit way. And really want to use real probing solutions because those are the physical ones, and if they're real, actually becoming more interesting than if they're not. You get harmonics of higher order and so on. And if f is not odd, okay, it's more complicated. So inverse problems for linear wave equations, of course, are very well understood. For example, you can consider potential here, and you know how to recover potential. If you send high frequency waves, you basically get the random transfer of the potential along the rays. You can recover a metric if you, this is the plausible trimy by the trial times. I mean, you know a lot about that. Okay, now about nonlinear wave equation. This is relatively new direction, maybe 3, 4, 5 years old. Actually, you can see here how old it is. And I'm talking about inverse problem for hyperbolic nonlinear wave equations. And the first work is this one that I'm aware of. And the main idea is to collide several planes, let's say 4 planes in time space, and this collision forms a source, and this source starts to expand, and then it comes back to you, and this source will tell you what happened at the moment of the expansion and the point of the expansion of the collision, actually. So here's some cartoon, okay? I mean, this is really the cartoon of what really happens. Of course, this keeps propagating after that, right? And then you stay somewhere here, for example, and then this comes to you, and it gives you information about what is going on in this point. That's the idea. This is based on this is not the idea that we're using. I just want to explain the history. So this is based on the higher order linearization, and you send several incoming waves with small parameters here, And then you look for expansion of our solution of this kind, and then somewhere you're going to have this term here. This is basically fourth order derivative, some very special one is 0. And you hope that this term, which is in the whole expansion, will give you information about nonlinearity. But for that, you need to send singular waves. They cannot be too singular because you have to be able to solve the equation after all. So they have to be weakly singular. So you really want to use to measure extremely small term, which is of fourth order basically. And in that term, you want to measure something like a very weak singularity. For example, a function which is C3, but it's not C2 or something or the other way, maybe something of this sort. Okay, so similar idea was used by several people, including me. You can use Gaussian beams instead of the ones that I mentioned, and you can send 3 beams instead of 4. They collide, and then they give you idea what is going on. Okay, so again, this is what is happening. So that term tells you what happened. But there are many other terms. There are maybe, I don't know, 70, 80 terms up to order 4, and you have to isolate this particular one, which is extremely small. And they collide and they propagate linear after that, and before they collide, they propagate linearly too. So advantage, you can target specific points and get point-wise inversion, but you really measure extremely small signal. And you really solve the equation in the linear region, basically. And some observations, so we observe the range of nonlinear operator, and that's a very rich object. And it's much richer than similar operator for linear equations. So you can expect that the information will be hidden in many layers, roughly speaking, and many levels. So this is a severely overdetermined problem. So if you linearize near 0, yeah, okay, you can do that. It can be done. It has been done. But then you could recover only f for general nonlinearity when u is close to 0. Right? I mean, because when you linearize, you basically get u equals 0, you can get a Taylor expansion. You cannot really touch u, which is away from 0. And you really want to probe with nonlinear value solutions. I mentioned that before because they're the physical ones in this context. And we probably want to send solutions that actually propagate nonlinearly, just for the fun of it. I mean, this is supposed to be nonlinear wave propagation. We want to see that. In other words, they shouldn't be too small. And the PD may not be even solvable on a fixed interval unless we have really small data, and we don't want to have small data. And PDs that model something interesting typically are solvable on some, roughly speaking, reasonable interval of time. Otherwise, we wouldn't study them. And very often they have some energy preservation, and that energy preservation helps to show that there's a global solution, or if not global, is on some reasonable interval, something of this sort. So in other words, we study equation that probably has some physical meaning after all. I'm not saying that the other people don't do that, but that physical relevance actually very often helps to actually achieve a solution that lives long enough. Even if it's not globally solvable, some solution may exist globally or long enough, and then we can use just those solutions. And we have to worry about solubility and stability of the direct problem as well, which is not a given for nonlinear equations, for even the direct problem. Okay, so now I start with cubic nonlinearity, the one that I mentioned before. We use nonlinear geometric optics. And let me explain quickly what that means. That was developed by many people. So those are the main people that I see in the literature: Rausch, Métivier, and Joly. And there are other. So this is different from interaction of classical singularities, which is quite hard and is due to a lot of people, including Buni, Melrose, Barreto, and so on. Right? This is basically propagation of semi-classical singularities and collision of them. So you have cubic nonlinearity of this sort. These are model now. Eventually, I'm going to make that more general. And assuming that the support of alpha is compact, we want to recover alpha. Okay, so if you just worry about uniqueness, it has been done by this higher order linearization, right? But you use extremely small solutions. And if you have some background noise of whatever nature, they will be completely lost there. So we don't want to do that. So we propose exploiting the so-called weakly nonlinear regime. And let me explain quickly what that means. So the qualitative behavior depends a lot on the balance between the amplitude and the frequency of the oscillations. So you can put here some epsilon in principle, but if you just replace it by power of h, you see h is the wavelength, more or less, and the amplitude is proportional to some power of h, just because we want to study solutions like that. And this is known in physics as weakly nonlinear regime under some conditions on P. We'll see that in a moment. But the point here is that if you start changing P, the behavior changes dramatically. So it's basically qualitative change of the behavior. So let me explain what happens. So again, I just copied the previous line here. So this is the form of the solution that we want to find. And the linear regime is the following. We choose P such that the economic equation stays the same as the linear case. And we can just choose a linear phase here for this purpose. And then the first transport equation in the linear regime is just the usual one as if that was linear. That's why we call it linear regime. We just really want those two properties to be like this, to be linear basically. And you're looking for a P that basically guarantee that. And the next one will actually be nonlinear somehow. And this happens when P is positive, but let's say P equals 0 is a standard choice to get classical expansion. In other words, that is the form of the solution if we really want on the principal level to be linear. And note that the amplitude is not small here. So I'm talking about linear regime, but this is not linear regime with small amplitude. Actually, it's the amplitude of 1, right? Okay, so again, I just repeat what linear regime here. And what is the weakly nonlinear regime that I actually used in the first part of my talk? Now you want the economic equation to be the same as before, but you want the leading transport equation to be affected by the nonlinearity. And if you just compute what P does this, it's -1/2 for cubic nonlinearity. And this is the transport equation, the first one, on principal level. And you see the nonlinearities here. And this actually system, if you write it for the real and the imaginary part of A0. And you see the amplitude is not small, actually grows with h. And the fully nonlinear regime is if you want even the economic equation to be affected. And very little is understood about that, so I'm not really going to talk about this. And now some examples. So those are some numerical computations. So you see a wave here, which is also oscillating in this direction and just cuts smoothly in this vertical direction. And you just let it propagate vertically. And this is the nonlinearity. It's basically some Gaussian. And you just let it propagate. And after a certain time, you just stop it, right? The solution just goes upside and then you just stop it at some time. In the linear regime, this just translates upside. I mean, of course, you cannot expect much more. You see the linear term, which is well linear. In the semi-linear regime, you see that something interesting happens here, right? So something changes. I mean, in the nonlinear regime, fully nonlinear, okay, you get some reflections, and actually I stop the time before it gets to the top, and it gets very messy. Okay, again, we don't really have very good understanding. Actually, nobody has about this case. We're not going to use it. We really want to use this regime. And here's animation. So again, the wave moves from the bottom to the top, and then somewhere here is the nonlinearity, the support of the nonlinearity, and then it starts to interact with this, and then you see that maybe it's still not quite clear, but there's some change of the phase, some phase shift, which is known in physics in principle. They call that phase self-modulation or something like this. And then you just stop at a certain moment. And you see that, okay, so let me wait until it stops. Okay, and you see that here, those wavefronts curve a little bit. In other words, you have a phase shift to the phase. It seems that the wave is moving a little bit faster there because it goes through the nonlinearity. And we're going to exploit this effect. So this is the incident wave that you sent. What you see there is the real part of it. And so we take the data to be the solution which is frozen at a certain time after most of it exits the domain. And then the theorem says that you have the following asymptotic expansion. So what goes out of the domain, it's of this sort. The leading term is like this. And this is what is due to the nonlinearity. If there's no nonlinearity, this will be just 1 because you have e to the power 0, right? And the nonlinearity is affected by that, right? This is alpha here. And if you look at this, of course, this is the interesting term. And the other is known. This is something to choose. And you see, this is the X-ray transform of alpha is actually involved in the phase shift. In other words, knowing this information, you can extract the X-ray transform of alpha, and then it changes the direction and so on. You can recover alpha. Okay, so this is the main idea of at least that part of the presentation. So a sketch of the proof, very fast, very quick one. Again, we're solving this nonlinear transport equation, which is actually a system for the real and imaginary part. But we can actually do the following trick. I mean, if you pass to characteristic coordinates, this is still not the trick, this is standard. Then we get this following ODE. I mean, still have a real imaginary part, right? And you can easily show that there is a so-called energy conservation. Just multiply here by A0 bar, and then you can treat this as a derivative of product or something of this sort. And then you see that that quantity is preserved under the solution. Now that's very simple, but very nice, because then actually this is constant, a real constant, and then you're actually solving linear equation. Really. So you can just solve it directly, and to get that. And what is A? Well, A depends on the initial conditions. And if you go back to the original coordinates and do all things carefully, this is what we get, right? So you get the following phase, and this is the original phase that you sent, and this is the phase shift here. And the phase shift is proportional to the Radon transform of alpha that you can recover. Okay, this can be generalized to Riemannian metrics and so on, so I don't have time to talk more about that. And let me show some numerical examples. So this is a nonlinearity. It's just take it to be a Gaussian. And then this is the initial condition. It moves to the top. And then this is the real part of the solution at time 1, right? In other words, this is your date. The big T now is just 1. And then what I do here is just take a cross section of that and plot it here. And you plot it against the linear solution. So the linear solution is in red or pink, brown, something like that. And the nonlinear solution, just for comparison, the nonlinear solution is in blue. So you see that there's some phase shift and also the amplitude changes a little bit. Okay, now you can just do absolutely the same thing, but decrease the wavelength by a factor of 2, and then you see the following. And the amplitude gets very close to the actual one for the linear one. And there's some phase shift as well, right? And that phase shift basically tells you, again, I'm plotting a cross-section, this cross-section here through the middle, right? So you can see that this is something measurable, so you can really measure it, you can compute it numerically. And this is the computed versus theoretical shift, okay, not bad at all. And okay, since I don't have much time, I'm just going to jump to the next slide. Now you choose alpha to be the shape logon, which is a very strange maybe choice for nonlinearity. Usually shape logon is used in medical imaging, but anyway, you choose it to be that function, which is plotted here. And then you see here the computed versus the theoretical shift in this direction. In other words, what you really see the X-ray transform in only vertical direction. And you see that there's something like Gibbs effect here. Yeah, you can expect that you don't have enough resolution to resolve really everything, but other than that, it doesn't look so bad. Okay, so now I mentioned before that you have to worry about well-posedness even of the direct problem. For linear PDEs, we just take it for granted more or less, but here you have to be more careful. And of course, we proved theorems that the direct problem is solvable and globally solvable and stability estimates, but of course there are some constants there that you don't really know very well what they are. And we just add 10% noise to the initial condition. Again, I talk about the direct problem, not even the inverse one. And this is what I get here. So you see the noise here creates some fluctuations, but that doesn't really look so bad compared to the previous picture. Of course, the Gibbs effect is still here, right? But I'm talking about the effect of the noise. It doesn't really destroy the data. And now global solvability, I'm going to be very quick. You can show that there is so-called energy in quotes, and it has this term here. And alpha is positive, I'm assuming that. If it's positive or non-negative, this is positive preserved so-called energy. And that really helps to show that this is globally solvable. And that's not quite trivial, but it's basically done in Ritten-Simon volume 3, maybe. You have to adjust some things and make some changes, but and it's done by other people before that. So it's a well-studied problem in principle. Okay, and this is a reconstruction of actual phantom. So it chooses to be very blurred because the resolution, of course, is bounded by the wavelength, at least, maybe it's even a little bit worse. And the wavelength is, okay, maybe something like this here, or half the wavelength maybe. And you see that the reconstruction a little bit blurrier, okay, but you can expect this. Okay, so now what if you probe with real waves, which is actually, if you really model something real, unless it is Schrodinger equation or something like this, you probably need real solutions. Okay, so if you send a real wave, which is just the real part of the previous one, of course, this is not linear equation. You're not going to get the real part of the previous solution, right? You get interesting things. The solution stays real, so you can just write the nonlinearity like this. And then this will not work because if you just assume that you're going to have expansion like this, yeah, they're going to fail because if you raise this to power 3, you get the frequency is tripled. And then you're going to be affected with nonlinearity again. So you're going to get actually a lot of harmonics. Well, okay, then your answer is not like this. I mean, you have to assume that you have the harmonics in the first place, which is well known actually in physics and also in mathematical treatment in this regime. So this is your answer, right? So you actually assume that the harmonics are there already. And if you just compute it numerically and plot that quantity, you actually can see the first harmonic, the third one, and the fifth one. You only get odd ones, which is very easy to understand. And the seventh one is not seen because I don't have enough resolution for it, but it should be here somewhere. And again, you take this linear phase, and the transport equations kind of similar before, but actually transport equations form a system. And that system is infinite dimensional, and it's not linear. Of course, this is discrete convolution, but it doesn't help so much to know that. So transport equation actually as hard to solve as the original equation. But we show that this is solvable in certain spaces, and then you show that you can still extract the X-ray transform from the expansion, but we only show that if alpha is small enough. Okay, so since I'm almost running out of time, I'm going to jump over this, but okay, here's the expansion. If you take the expansion first, h is small, of course, so you ignore this remainder for a moment. And if you even linearize near small alphas, then you get the random transform here, you get it there, but this is enough. Okay, so back to comparison with how it works. Again, instead of trying to extract some very small term among many other terms, what we do is send a wave of this magnitude and to measure a wave with the same magnitude, but to measure is the phase shift. And from that, we extract what you want to extract. So this can be generalized, as I mentioned. And I'm going very fast because I really want to have some time for the second part. What about general nonlinearities? And this is recent result with Antonio. So if n is f is out in the u variable, so if it's like this, and the probing wave is real varied, which is actually the most interesting case and the hardest case. We didn't even bother with the complex case anymore. We have unique and explicit recovery, which is quite interesting and is very different from what I talk about. And now the idea is the following. So you want solutions that are not small or not large. So before we had here h3 power minus 1/2. Now we don't want to have this, because if you have large solution, the large solution will basically test this function for large u. And what happens for u equals 1, for example? Okay, it's not going to fill it so much. If the solution is very small, it's going to test the solution for u equals 0. You want solutions that basically test this function for any u. And in other words, we take solutions like that, and we can play with that function. We can take the maximum of this function to be a parameter. So of course, you can basically include parameter k here for free, because you can take different k's. And if you play with that parameter, then you feel, roughly speaking, the nonlinearity at different levels. Okay, so this is the main idea. And we're in the linear regime, but not too deeply. In other words, the principal term is linear, more or less. I mean, it's like in the linear case, to be more precise. But if you go 1 degree lower, then it's affected by the nonlinearity. This is very similar to potential scattering. It's exactly what happens there. And now take this, insert it in the nonlinearity, just to see what happens. And just ignore this for a moment. And then you get something like this. And then if you have a complex probing wave, which we don't really want to do, but if you had this, and if you had a model square here, right, then this would just disappear. It's going to be 1, and then you really have a potential, basically. And then we know what to do. But you don't want to do that. You don't want to have complex probing waves. So this really oscillates. And well, what do? We just expand this in Fourier series. So expand that thing in Fourier series, well, cosine series, because of even odd properties, in terms of variable theta. What is theta? Theta eventually is going to be that. And this is the same as to expand this function in Chebyshev polynomials on the interval -1, 1. I mean, it's equivalent thing, and we know how to do that. We do it. Those are the Chebyshev coefficients. And then look for expansion, which has all the harmonics and so on, right, as before. And we put this in the equation and so on, and then we see that we can relate those Chebyshev coefficients, and those are the Chebyshev polynomials, right, with we can solve it for them, basically. And here's the main theorem. So this is the main expansion. This is what you sent. And this is the next term, which is of degree 1 relative to -1, if you wish, relative to the previous one. It has expansion like for a series, but then here you have the extra transform of the Chebyshev polynomials, well, coefficients to be more precise, in terms of the x variable. And that you can actually fix it, because you can take the data at different levels. So this can be any fixed number, and then you actually get random transform again, which you can invert and so on. But instead of doing that, actually you can do better. You can just take the first harmonic here, only k equals 1, which will be the first harmonic. In other words, this will be the main frequency that you send. Ignore the higher harmonics, and you can show that that which you can recover by inverting Fourier transform is related to the nonlinearity by this Abbott type of equation, which actually can solve precisely. Yeah, for some reason, the formula here disappeared when I was working on my file. But anyway, there's a formula for the solution, right? This is a standard equation. So there's actually a direct formula for the solution of F0 in terms of gamma 1, which you can recover from the previous step. So you don't need the higher harmonics. And some numerical examples, I mean, I started in 35, right? So I have 2-3 more minutes, I guess. So in some numerical example, this is a cubic nonlinearity which we treated with the previous method, but now we have a different method, right? Just for the fun of it, see what happens. And this is a cross-section of U, which is the solution. And this is basically the linear solution because the non-linearity effect is in the lower order terms. And this is the next order term, which is divided by H, otherwise it will be too small, and divide by the random transform of, which is the whole point. You want to extract it just to see if you can confirm the formula. And then you see that, yeah, you can confirm it. So the theoretical maximum should be 0.79, and this is quite close here. And if you plot the spectrum, so you see the first and the third and the fifth harmonic, but the idea is you can extract everything from that. And now you take a non-linearity like this. Now you have a linear part actually plus cubic part, and I choose the coefficients such that you really see the effect of higher order harmonic, because in the previous case you couldn't see them. And this is the theoretical profile. I mean, see that interesting part, and this is the computed one. Again, this is a vertical cross section, right, as before. And it's quite close. I mean, it's not quite the same because numerically, wave equation doesn't behave very well if you try to propagate it too long, too far, and very small frequencies, but it still looks okay. So it was done on a really high grid, 4,000 by 4,000. And now, what if the non-linearities are not out? Okay, let's just say it's more complicated. So you get zero order harmonic. This is called rectification in physics. And that actually appears in the principal term instead of the sub-principal one. A little bit unexpected. And then you get also the sub-principal one, but you get this zero order harmonic, which doesn't depend on H, doesn't oscillate, right? It's just a fixed solution. And actually that makes the inverse problem more complicated. And since I don't have time to do this, I'm just going to show those pictures, and I'm going to stop here. This is the harmonic that we see, the zero order harmonic that I mentioned. I just removed the principal part because if you plot this, it will basically dominate over everything else. So this is removed. And then this is what we get. This is the zero harmonic that we didn't have before. And if you remove it, actually, I can really show that those terms really appear there and they really correspond to the theory. But I want to stop here because I don't want to take more of your time. And for that, you can show that you can recover alpha for non-linearity, which is just quadratic. Of course, you have to be careful with the existence there. Alpha has to be small, otherwise it may not even have solution. And if you have polynomial of finite order with respect to U, you can still do it. But if you have more general one, which is not odd, then this zero order harmonic is really a problem for solving the inverse problem. Okay, I'll stop here.
Okay, thank you very much. And colleagues, any other questions? Well, colleagues, any questions?
Максим Александрович, могу задать вопрос?
Да.
Excuse me, thank you for your talk. The question is the possibility to move this technique onto the hyperbolic systems? Is there any related works? Are there going to be any difficulties?
Actually, the nonlinear geometric optics that I mentioned at the beginning by Julie and Metivier, I'm trying to find the slide, was really done for systems. Also, Runge, I should have mentioned him, he has even a book about nonlinear optics. Yeah, okay, it will take me too long to go to the beginning. So there are a series of papers, maybe 7, 8, 10 papers, and the whole book. And Métivier has notes which are, I don't know, 80, maybe 100 pages, which is almost a book. They actually do it for systems. And their main interest is Maxwell, nonlinear Maxwell, with different nonlinearities and so on. So in principle, yes, that would work for systems. Of course, it has to be done, right? And you have to have the right assumptions and so on, but the machinery that you need is available for systems. At least for the first part of my talk, which was cubic or modular polynomial nonlinearities, right? For the second part, I'm not sure, right? But for the first part, because for the second, what is really important here that you don't really have derivatives in the nonlinearity. Because if you have derivatives, things change. And if you want to convert this equation to a system, right? Let's say you want to include here ut and ux. Yeah, if you want to convert this, first, all those techniques have to be modified because if you have high frequency solutions, that is going to be much larger than this. And if you want to modify this to a system, so some derivative may not be derivative, who knows. But my point is that if something can be done, all the machinery is there because those techniques about weakly nonlinear regime were actually developed for systems. So they're available.
Okay, thank you very much.
Okay, thank you very much. Well, colleagues, any other questions?
Hello, may I ask a question?
Yes, please.
Okay, yeah, I'm just a little bit been late, but on some previous slide you showed the Abel integral equation. Could you please come back to this slide?
Which one?
Oh, with the Abel type integral equation.
Oh, Abel type. Okay. Let me try to go there. Yeah. When you use PowerPoint, it's slow to navigate. I will get there. Okay, I'm close. Yeah, okay, that's it. Yeah.
Yeah, I'm just wondering why on the top of the limit is 1. So just conventional Abel integral equation should be x, maybe not. I'm just a little bit confused. Yeah, please.
Right. I mean, it comes from the Chebyshev polynomial and so on. Of course, here you have 1 minus q, right? You don't really want to go above 1.
Yeah.
Yeah, but of course you can always make change of variables, right? You can just make change of variables mq equals, I don't know, s, for example, and that will change. And then really solving Abel equation.
So the limits are fine. That's the integral from 0 to 1. Yeah, that's right.
Yeah, it is correct because again, 1 is where you have singularity, so you have to stop at the singularity.
Okay, I got it. Yeah.
Right. I mean, really, you have to stop here, right? So the limits are right, and you rescale the variables and you reduce it to Abel equation and so on.
Okay, it's clear. Yeah. Thank you.
Well, thank you, colleagues. Any other questions? Well, if there are no questions, so Professor Stefanov, thank you very much for your interesting talk.
Okay, thank you. So let me unshare my screen. Okay, so stop share. Okay.
Well, and the next speaker is Professor Quinto.
Hi, I'll be sharing in just a sec. There we go. Good. Well, I wanted to thank the organizers for a really interesting conference. I've enjoyed both talks, and I look forward, at least when I'm not asleep, to some other talks. This is joint work with a young colleague of mine, James Weber, who was at Tufts and is now at Brigham and Women's Hospital doing machine learning research. And this is supported by the US National Science Foundation and the Simons Foundation. Good. And what we're going to do is analyzing a class of radon transforms that integrate over surfaces of revolution. And so this could be just a classical problem, but this is motivated by applications, which I'll explain in a little bit. And we find conditions, under which they're well behaved and satisfy something called the Volcker assumption. And then we'll analyze reconstructions from our models to show what they do with singularities and what happens when this assumption fails. Good. Well, they're solids of rotation, so we use a defining function, a continuous function from 0 infinity to itself that starts at 0. And we're going to use Q to define the surfaces of revolution. And so we take a point in Rn and just break it up into the n-1 and n coordinates. And the center or base of our cone is going to be in Rn-1, and E is just a real positive real number that represents the energy in our models. Okay, and our transform will integrate over this surface. We take the points in Rn such that the nth coordinate is this constant E times this function Q that we defined. It defines the radius. And so let's look at a picture of that. So here's the object, and so we take a point x0, and then let's say r is the distance from x0 to x prime, and we take E Q of r. And that gives us our point, and then we get, of course, our surface, and it's symmetric, and in Rn, it's just the surface of rotation, so nothing cosmic. Good. And our radon transform is going to integrate over integrate over this surface S of Ex0 in Rn of the function f with respect to surface area measure. Good. And the applications are in transmission Compton scattering tomography. What will happen is parallel beams will come into the object, and then they hit something, maybe here, and then scatter. And all the ones that scatter with the same energy will go along will go along a parallel line. So some of these go over here, but the point is some of them go on this line here or this line, and what it tells you is the number of scatterers along these broken rays. And in R3, of course, it's just a cone. So that is one model, and it's standard and well understood. And what we're going to talk about is well known for this, but it's not well known for so the energy adjusts the V-line opening angle, because the smaller E is, the flatter it is, and is determined by the scattered energy measured at the detector. Good. Now, a new methodology is Bragg scattering tomography, where now this surface represents the surface of integration for a standard model in Bragg scattering tomography. And I refer to this article in Inverse Problems in Imaging that appeared recently, I think last year. And the point is the function that we have that defines it is not just linear, whereas with the parallel beams, it is linear. And so we get pictures. The broken ray transform is in red, and that's for the Compton scattering tomography. And these curvy things are in blue, represent Bragg curves. And these curves, of course, are scaled by E and translated by the point x0 along Rn-1. And you get more integrals of the object. Okay. Important work in Compton CT. There are a lot of really good articles on V-line and conical transforms. And here are just some of the people, Bartsumian, Christian, Kuchman, Emnun, Shotland, Sergolo, and others in the spindle-torus transform, which is another type where the source can be fixed and the detector is also fixed. And then you integrate over either lemon-looking things or sort of, they call them apple-looking things. And Simon Arridge, Holman, Bernadette Hahn, Rigaud, Weber, and so on. And then in Bragg scattering tomography, I'm not aware of as much, but the article of Weber and Eric Miller of our electrical engineering department have talked about that, Klug and Alexander. But these are all rad-on transforms, and I want to make the point that there are a lot of really important articles and researchers on this, including, of course, Israel Gelfand, Simon Gindikin, and Palamodov, and many others. Of course, Stefanov and Ullman, and many people both in Russia and the former Soviet Union in the old days, and elsewhere. Good. Okay. I'd like to digress for a little bit and talk about smoothness. This is something that some people might know about, and so spoiler alert, it has to do with the wavefront set. But it's an important question how to recognize smoothness of functions and how to characterize them in a way that's useful for proving things and useful for understanding singularities. Okay. And we're going to use the Fourier transform. So if we have a distribution of compact support, it's going to be smooth everywhere in Rn, if and only if its Fourier transform decays rapidly in infinity in all directions. In other words, of y, let's say, is always less than or equal to some Cn 1 plus norm y to the n. For every n, you can find a Cn. And so that it just means it goes to 0 very fast. And it's a simple argument using the Fourier inversion theorem. And so I won't sketch it. But this is a global thing. In other words, if you analyze the Fourier transform of f, and say that it rapidly decays, then you know f is smooth in all of Rn. That's not local. Singularities are local. So we localize at a point, and this is very standard. We take the point and we find a bump function that's non-zero near x0 and 0 outside of a little neighborhood of x0. And so we take a function phi in D, namely C infinity functions of compact support, not being 0 at x0, and see if the function is smooth. That'd be one thing to do. And if it's smooth, then f is smooth near x0. But we can do something more subtle. We do what we call microlocalize. And that is, we take a direction, C0, and we look at the Fourier transform of phi f, and we don't ask whether this localized Fourier transform decays everywhere, but we just ask whether it decays in some conic neighborhood of C0. It could not decay outside of that neighborhood, but if it decays in that neighborhood, we have an idea that the function is smooth at the point x0 in this direction, C0. Good. So that's the idea of our next definition. And I'm taking it from Trev's from his 1980 book. There are a lot of other references. I'm going to say that f is smooth at a point in a direction if there's a smooth cutoff function. That is, we're going to localize. And there's a conic neighborhood V of C0. And this is the microlocalization such that the localized Fourier transform decays rapidly in this. Okay, and so then we'll say that f is smooth at x0 in this direction. Okay, and then if not, we'll say that x0, c0 is in the wavefront set of f. So that's points where it's not singular. So what's cool is wavefront sets simultaneously describe the location, namely x0, and the direction, c0, of each singularity. So let's see an example. Let's take the characteristic function 1 here and 0 here. And the places where it's singular, it's obvious, it's the boundary. And for each point on the boundary, the wavefront set, if the boundary is smooth, picks the normal direction. And this is sort of the direction in which the function is least smooth. If I walk in this direction off, I fall really fast. If I maybe walk tangentially, I might not fall at all. If I'm walking on this and it's 1 unit above the plane, the XY plane. So anyway, that is the point, that the wavefront set is the set of normals to the boundary. And in order to make it invariant, they use the cotangent bundle because then it's invariant under change of coordinates. But for simple functions like this and in Rn, you can just imagine either the tangent bundle or just this vector bundle. Okay, good. Good. Okay, let's review. For x and Rn, we write x prime, x prime and xn in our set. The surface or hypersurface in Rn is this. And we take a point or in R plus cross Rn minus 1 that we call R plus cross Rn minus 1, we call y. And we define this function here. In other words, it's 0 on the cone, when xn is equal to this thing on the right, then psi is 0. So psi defines the curve, or the surface, I'm sorry, the surface S. And so the Radon transform can be written as a Dirac delta of psi times this weight that gives you the right measure on the surface. And it can be rewritten as e to the I sigma, that's the Fourier variable in one variable, times psi, this doesn't change. And I'm just using this fact that is a distribution, the Fourier, inverse Fourier transform, well, of 1 is delta. Okay. Now, this operator here is a special type of operator called a Fourier operator. And that's part of the simple part of our main theorem. Okay, so getting back to our Q, we let Q go from 0, infinity, 0, infinity, be continuous in the closed interval, and C infinity on the open interval. Start at 0. And here we have a new condition, Q prime is positive, so the function Q always increases. So our surface doesn't go down and then up, it just goes up all the time. Then R is an elliptic Fourier integral operator. Now, this operator I wrote on the right here is the form of a Fourier integral operator. And what we check is that this psi is a regular phase function, and that under our assumptions, this weight is never 0. So it's a Radon transform with non-zero weight, so that makes it an elliptic Fourier integral operator because the phase is a clean phase function. Good. And now then, if you don't know about Fourier integral operators, the important thing is that wavefront set of F, causes is too strong in general, but the wavefront set of F affects the wavefront set of RF. In other words, the wavefront set of RF is contained in some relation to the wavefront set of F. This C is the local canonical, is the canonical relation of the Radon transform. But if you don't know that, it's sufficient to just say that knowing the wavefront set of F and knowing some relations well defined by psi, you can say that the wavefront set of RF doesn't go outside the right-hand side here. Good. Okay. Now, this is pretty standard. Now, we decided in our article to define this extra function, Q prime over Q. The next thing is R satisfies a very important condition. I'll explain why in a minute. If and only if this simple equation, ln of Q double prime, which is G prime, is never 0 on R plus. Now, the Bolker condition is, as you can see down at the bottom, the left projection going from the canonical relation to T star Y is an embedding. But the important thing for us is it means that if you take a smooth cutoff on Y and form a normal operator, R transpose, the back projection, this, phi R, phi is there so you can compose them. It's a pseudodifferential operator. Pseudodifferential operators have the good property is that they don't add wavefront set. They the wavefront set of RT phi RF is contained in the wavefront set of F. By the little arrow, I'm just saving time because I see we're nearing the end. Good. Okay. Now, what's interesting about for applications is both this broken wave transform in Compton scattering tomography and the Bragg scattering transform satisfy our theorem. So these transforms satisfy the Volcker condition, and that means the normal operator is the well-behaved operator. Now, it already was well known that the broken ray transform does, but the Bragg transform is new, and so that's the new part of our result. Okay, good. And the proof outline, let's see. I think I can give you the basic. You describe our surface in terms of spherical coordinates because it's a surface of rotation, so it's natural to do that. Then you get coordinates on the canonical relation, and those coordinates allow you to learn whether pi L is an injective immersion. And we use the fact that G prime is never 0, and it reduces to a 2D problem related to G. And I said if and only if we just observe at the end that our proof is if and only if. Good. Okay. Here's some examples. Here are the broken rays. This is, okay, I take the characteristic function of a ball. The ball is sitting here. Well, my ball is not very good, but you can see the ball in the middle here. And this is the so-called Lambda tomography reconstruction, where I take the data, R of the characteristic function of the ball, take a second derivative in the energy, the E, and back project, and then I get this picture, which sort of looks like a ball, but there are these streaks which come about not because, well, come about because we in our reconstruction didn't put the phi in. If we put the phi in, we could have suppressed those really easily, but somehow it didn't happen. And don't blame me. And then my colleague did Landweber reconstruction, which recovers the inside better. I mean, that is, it looks like an inside. And here are the data. And if you look at the boundary of the data, there are singular points on the boundary of the data, singular points of the function. And in this case, we get artifacts, and it's predicted by an article of Borg, Frickel, Jorgensen, and myself in 2018. Good. Okay. Because we're integrating over lines, that's the relation to this. Good. Okay, for the Bragg curves, we have these weird curves, and we have the same object, and we do the same types of reconstructions, but with R being the Bragg transform and R star being the back projection for Bragg. And if you look carefully, you can see streaks that are actually Bragg curves at the ends of the data that are tangent to the object, and you see them here in the Landweber. And it's a similar reason to the one in our article about X-ray CT. Okay, here's what happens when Volcker doesn't hold. We're taking basically the Dirac delta, and here are curves, and you can see that they don't actually increase strictly everywhere. And it's wild. You get a lot of extra singularities because the Volcker assumption doesn't hold. If you had put, yeah, right, Volcker doesn't hold. And it would even happen if you'd smoothed out the singularities of the boundary of the data set. Okay. Great. So this appeared in Sims this year, just a little bit ago. And in the article, we provide conditions in which a radon transform untranslates at the surface of rotation satisfies the Boltzmann condition. So it applies to many other things besides the two practical examples. And we show that these Compton CT and Bragg CT satisfy this. And we also prove Sobolev continuity. And we also characterize in Sobolev space the visible singularities that follows from microlocal arguments and Sobolev continuity in broad. And we're working on 3D Compton problems now. And for those who don't know Russian, I have English on the right. Spasiba. Thank you all very much.
Okay, thank you very much. Colleagues, any questions?
I have a question.
Yes, please.
Yeah.
So if you go back to those lines there that change the angle and change the base point, I believe, right?
Let's see.
Just the picture, yeah, the previous slide.
This one?
Yeah, right. I mean, those lines, the other one with the lines, right? Did you show the lines?
Oh, yeah, gotcha. Okay, sure.
So which are the parameters that you change there? So just x, the base point moves horizontally and the angle changes?
Exactly.
But they're just a subset of all lines, right? I mean, so
Yeah, I know. And that's why but the difference is if you had a big object, then it would be affected by both. So it's not just limited angle. Although your point is that when we get over here, streaks are really just limited angle streaks, or sorry, limited data streaks.
Okay.
Yeah, good point.
Right, okay. And
Yeah.
in the other one that you showed with those curly lines.
Yeah, right.
Okay, so they're probably artifacts that are due to both. First, there's a boundary in your set, and their conjugate points as well.
Mm-hmm.
So they're two
Well, the conjugate points, there aren't, because Volcker holds there aren't conjugate points, if I understand what conjugate points are.
Right, yeah, basically that. But you also have boundary of your data, right? As in the
Exactly.
previous. So they somehow mix together.
Mm-hmm.
Okay.
And in the but speaking of what I think you mean by conjugate points, this one big time, yeah. Anyway, I was thinking of selling it as a T-shirt, but anyway, yeah, great. Any other questions? Thank you. Yeah, thanks, Paul.
Well, any other questions? Well, so if there are no questions, so Professor Quinto, thank you very much again. And
thank you.
So, okay, thank you. So we organize our conference in mixed format, I mean, online and offline. So now we have a coffee break for 20 minutes and we will start at 11:05. So we have a coffee break for 20 minutes. Okay, thank you.